2.9 dimension and rank. Coordinate systems. Suppose that the set B, is B1 to Bn, is the basis for the subspace H. For each x and h, the coordinates of x relative to the basis B are the weights C1 all the way to CP, such that x is C1 times B1 plus all the way up to CP times BP. And the vector in RP, x is R1 to Rn, is called the coordinate vector of x relative to B, or the B coordinate vector of x. Example 1, let V1 be 362, V2 be negative 101, X be 312, 7, and H equals span V1, V2 because V1 and V2 are linearly independent. Determine if X in H is in H, and if it is, find the coordinate vector of X relative to B. So there should be a fancy B there, or beta. So with this, if X is in H, then the following is consistent. C1 times 362 plus C2 times negative 101 equals 312, 7. The scalars C1 and C2, if they exist, are the B coordinates of X, and row operations show this. So we would be able to row reduce this down to thus C1 equals 2 and C2 equals 3. And my coordinate vector of X relative to B is 2, 3. And this is the basis B determines the coordinate system on H. And see this figure here for that. Dimension of a subspace. The dimension of a non-zero subspace H is denoted by DIMH, so that's dimension, is the number of vectors in any basis of H. The dimension of the zero subspace 0 is defined to be 0. The rank of a matrix A is denoted by rank A, is the dimension of the column space of A. Example 3. Determine the rank of the matrix. So we're going to take this matrix A and reduce A to echelon form. I'm not going to go through all the steps. I'm just going to go through and give it to you. So it's 2, 0, 0, 0, negative 5, negative 3, 0, 0, negative 3, 2, 0, 0, negative 4, 5, 4, 0, and 8, negative 7, negative 20, negative 6, or 0. So here we have 1, 2, 3 pivot columns. The matrix has 3 pivot columns, so the rank of A is 3. Theorem 14, the rank theorem. If matrix A has n columns, then rank A plus dimension A equals n. Theorem 15, the basis theorem. Let H be a p-dimensional subspace of Rn. Any linearly independent set of exactly p elements in H is automatically a basis for H. Also, any set of p elements of H that spans H is automatically a basis for H. The invertible matrix theorem continued from section 2.3. So let A be an n by n matrix. The following statements are each equivalent to the statement that A is an invertible matrix. The columns of A form a basis of Rn. N, column A equals Rn. Dimension of column A equals n. Rank A equals n. Null A equals 0. And the dimension of null A is 0.